Okay, welcome to this video where I talk about the problems to do with refraction through lenses. Mainly we're going to talk about the convex lens, which is a converging lens, and the concave lens, which is a diverging lens. We will also talk about the eye defects and how they can be corrected using lenses, and a little bit about optical instruments, chiefly the telescope. This first question talks about a negative 8.5 diopter, let me make it 8 diopter lens is held 12.5 centimeters from an object 1 millimeter high. What are the position, type and height of the image? The power of the lens is given, and the unit of power is diopters. That is the reciprocal of the focal length in meters. So power is 1 by focal length. Therefore focal length is 1 by P, so that's 1 by negative 8. And that is negative 12.5 centimeters. Because 1 by 8 is going to be 0.125 meters, right? So that is negative 12.5 centimeters. The negative sign there shows that this is a diverging lens or a concave lens. And to find the position of the image, use the lens formula. DO is the object distance, DI is the image distance, and F is the focal length. We're looking for DI. You can substitute this directly into a calculator and get the answer, but I've just tried to make DI the subject. That gives minus 6.25 centimeter. The negative sign shows that it's a virtual image. Now to find the magnification, use the formula HI by HO, which is equal to minus DI by DO. The height of the object was given, that's HO, and we have DI and DO. And since there are two negative signs, you're going to get a positive. When the magnification is positive, that means it's an upright image and it is a virtual image, because only virtual images are upright. In this question, it's a 105 millimeter focal length lens used to focus an image on the film of a camera. The maximum distance allowed between the lens and the film plane is 132 millimeter. So that's going to be DI. How far ahead of the film should the lens be if the object to be photographed is 10 meters away? So the object is 10 meters away, that's DO. And then you have B and C. Okay, so you have the lens equation again. You're given the focal length and you're given the object distance, and we're trying to find the image distance DI, as in the last question. Now I've converted 105 millimeters into meter, and that's also in meters now, so you get 10.6 centimeter. Same thing if the object is 3 meters away, just in place of 10 substitute 3 and then get the answer. Likewise for 1 meter away. But notice that as the object distance changes, the image distance changes slightly. Do you see that? It's When the object was 10 meters away, the image distance was 10.6. When the object is 3 meters away, it's 10.9. And then when the object is really close, 1 meter away, it's 11.7. So this is why it's easy to focus a camera, because even when the object distance changes drastically, the image distance only changes slightly. Now the D part says, what is the closest object this lens could photograph sharply? Once again, we go to the lens formula, but now DO takes the minimum value. That means DI takes the maximum value. And the DI maximum is 132 millimeter there. So find DO minimum with that maximum value. Just 132 millimeters. 13.2 centimeters, and the focal length is 10.5 centimeters. Remember that all of these are in centimeters now. And you get 51.3. So if the object is closer than 51.3 centimeter, the picture cannot be taken using this camera. Number 3, how far from a converging lens with a focal length of 25 centimeters should an object be placed to produce a real image which is the same size as the object? Now that's the important point. Same size as the object. That means the magnification is 1. Another thing is, it's a converging lens. And we are asked to find how far should the object be placed. DO. We're looking for DO. Once again, the lens equation. And we know that DI should be equal to DO. And I'm going to prove that. And so in place of DI, we can write DO, as I've done, and then from there find DO as twice the focal length, so 50 centimeters. Now, as I told you, magnification is negative DI by DU, and it's given as 1 in this case. It's negative 1 because it's a real image, right? It's negative 1 because it's a real image. So put negative 1 is negative DI by DO, which gives DI is equal to DO. That's why I use that in order to calculate DO. Now that should make real sense. Number 4, how far from a 50 millimeter focal lens must an object be placed? So again, you're looking for DO. If its image is to be magnified 2 times and be real. So that means the magnification is going to be -2. Because real images have a negative magnification. And then the second part, what if the image is to be virtual and magnified 2 times? So in the second case, magnification is going to be +2. That's the difference, right? And in each case, we got to find DO. So again, for a real image, this is a converging lens. That's why it's able to produce a real image. So therefore, focal length is positive. And DI must be positive because magnification must be negative. So M is negative DI by DU. Magnification is negative. Oh, I'm using 2.5. So the question says 2, but I'm using 2.5 and it's too late to change it now. So please note that. Okay, DI is 2.5 DO. Now use the lens equation, because in place of DI we can write 2.5 DO, which is exactly what I did. And then from that if you make the focal length the subject, you get that, because you have a DO squared and a DO. So from there, rearrange and find DO as 70 millimeter. Now the B part, if the image is virtual, therefore the magnification is positive. DI is negative minus 2.5 DO. Okay, right from here, it's going to, but the only difference, DI is negative, so it's negative 2.5 DO. Put it back into the lens equation carefully and you calculate DO. $30 millimeter is the answer. A 2.8 centimeter high insect is 1.30 meter from a 135 millimeter focal length lens. Where is the image? How high is it and what type is it? B part, what if f is minus 135 millimeter? Straightforward question. DO is given 1.30 meter. The focal length is 0.135 meter. You have to find DI. That's DO. That's the focal length. And when you calculate, you get 0.1506 meter. Magnification is HI by HO, which is negative DI by DO again. So make HI the subject, and you get minus 0.1506 by 1.30. So get negative 0.324 meter. In the B part, same formula. It's just that the focal length is now negative, so that's negative there. That means it's a diverging lens. And you get minus 0.1223 meter. Magnification, again, same definitions, and make HI the subject. .263 meter. Okay, remember that in the first case, it's a real image because magnification is negative, but in the second case, it's a virtual image because magnification is positive. Reading glasses of what power are needed for a person whose near point is 105 centimeter so that he can read a computer screen at 55 centimeter? Assume a lens eye distance of 1.8 centimeter. Now, this person has a near point at 105 centimeter. For a normal eye, the near point is about 25 centimeter. But this guy, he has it at 105. But he needs to read a computer screen which is much closer at 55. So his problem is what is called long sight. He cannot see any object clearly which is less than 105 centimeter from his eye. He needs to wear converging lenses to correct this. And the screen is placed actually 55 but 53.2 centimeter from the eye. 53.2 centimeter from the eye lens. And the virtual image must be produced 105 minus 1.8 centimeter. So the idea is that when the object is 53.2 centimeter, that lens that is wearing should produce an image which is 103.2 centimeter from the eye lens, so that his lens in the eye can take it up from there. Okay. Therefore, the power of the lens is 1 by focal length, given by the lens equation now. That's in meters. Now both of them are meters. You get 0.91 diopter. So you see it's positive. That means it's a convex lens. So the person must wear a convex lens of power 0.91 diopter. Now this person's left eye is corrected by a minus 4.5 diopter lens, so that's a diverging lens. That means he has short sight, and 2 centimeter from the eye is where his lens is kept. Is this person's left eye near or far sighted? Near sighted. What is this eye's far point without glasses? Which means how far away can he see without glasses? All right. So he is nearsighted because the power is negative. That means it's a diverging lens or a concave lens. He can see objects that are close, but he cannot see beyond a certain distance. So when the object is at infinity, the image is produced at his far point, right? Okay, so that's what I've written now. The far point is the image distance for an object at infinity. So when he wears those glasses, the glasses help him to see up to infinity. Why? Because the object at infinity, his glasses will produce the image at his far point, and then the eye lens will take it over from there. Okay, DO is infinity, and then when you use this, remember 1 by focal length is power, so I've directly put that there, and you get minus 22.2 centimeter. But since the lens is 2 centimeter from the eye, that's why we've considered the 2 centimeters. So actually, it's 24.2 centimeter from the eye. Okay. A person's right eye can see objects clearly only if they are between 25 and 78. What power of contact lens is required so that objects far away are sharp? Or what will be the near point with the lens in place? So this person can only see objects between 25 and 78. And the question is, he must be able to see objects at infinity. Okay, so DO is infinity. DI is 0.78 because if the glasses can produce an image of the object which is at infinity, if that image can be produced 78 centimeters away, he can see it because his eye lens will take it over from there. Using the lens formula again, and DO is infinite. Remember that DI is negative because it's a virtual image. You get the power of the lens. What will be the near point? Remember that the closest distance you can see is 25 centimeter. We're going to use that now to find DO. There's a little bit of calculation there. That's the power multiplied by DI. Again, di is negative because it's always virtual images that you can see. So his near point is going to be 37 centimeters. And that brings us to the last one. An astronomical telescope has an objective with focal length 75 centimeter and a positive 35 diopter eyepiece. What is the total magnification? Now, in a telescope, if you're looking at objects far away, the rays are parallel when they are incident on the objective, and the objective produces the image at its focal point or in the focal plane. And then if the focal point of the eyepiece is exactly at the focal point of the objective, then the final image will be produced at infinity, in which case the eye is relaxed and the formula for magnification is minus FO by FE. And 1 by FE is the power, so I've rewritten it this way. Magnification is going to be minus 26 times. And here you see how the objective first produces the image of an object at infinity exactly at its focal point. You see the FO there, but the eyepiece also has its focal point right there. So this image behaves like an object for the eyepiece, and the final image is produced at infinity. So the rays fall on the retina, but they seem to be parallel. Therefore, the eye is relaxed and thinks that this image is at infinity. So hope you make good use of these problems in the preparation for your exam. And thank you. Good luck.